This is section 4.1, linear functions. So we're going to look at, well, linear functions, but basically just straight lines, but with function notation. So instead of y, we'll use f of x. And then we'll look at some applications. So really most of this is going to be the application side of things. So let's go ahead and jump into objective 1 here, represent a linear function. So the definition, f of x is equal to mx plus b. M is a constant, and obviously that's the slope. We've seen that before, but it's we're going to think of it now as also the rate of change. So that can be a speed, it can be like a price per item, or even a percentage, like an interest rate or tax rate. And then b is the initial value. So we've thought of that as our y-intercept, but it is in some sense like the starting value of the function. So maybe like a base price or starting distance or something like that. So example 1, consider the first commercial maglev train in the world, the Shanghai maglev train. It carries passengers comfortably for a 30-kilometer trip from the airport to the subway station in only 8 minutes. Suppose a maglev train travels a long distance and maintains a constant speed of 83 meters per second. 83 meters per second. Once it is 250 meters from the station. 250 meters from the station. Write a function that gives the train's distance from the station as a function of time. And so maybe it's not completely clear here, but we're going to write our function using the starting value being this 250. So starting at 250 meters is when we get that constant rate of change, meaning it is linear. We can do that mx plus b form. And since I've got this little table down here, let's try and be consistent with that. So instead of x, I'm going to use t, and instead of f, I'm going to use d. So t for time looks like seconds. So t is number of seconds. And then d for, that would be meters. Meters from the station. So d of t is our rate of change, our m value, 83 meters per second, so 83, times t, the independent variable, and then plus our initial value, our initial distance from the station. So this would be the answer right here. And so if you look at a table of a linear function, it's always going to show you how you have this constant change. So if you increase your independent variable, what we think of as the x, but in this case t, by 1, this distance increases by 83 meters per second. So if we increased by 2 seconds, it would increase our distance by whatever 83 times 2 is. I don't know. What is that? 166. Is that right? I don't know. But anyway, no matter what kind of increase in t you have, you should have a corresponding 83 meters per second if you sort of like divide it out. If for some reason after, I don't know, 3 seconds, it all of a sudden jumped up more than 83 meters to the next second, that wouldn't be linear. I don't know if that makes sense. Let's look at example 2 to see kind of another example of this. So a new plant food was introduced to a young tree to test its effect on the height of the tree. The table shows the height of the tree in feet x. So this is, height of the tree in feet x months. So this x is months. Here. I don't know why I need sound effects for my erasing. Okay, so x months, and then this is feet, h of x, h for height, I guess. Is this function linear, y or y not? So this one's tricky because we're not maintaining the same difference for our x's. 0 to 2, we're adding 2. And then to get to 4, we're adding another 2. So far so good, but then it switches to plus 4, plus 4. So it's a little weird to figure out if we're going to have a constant rate of change. So let's just go ahead and put in here what the difference between each pair of h values is, heights. 12.5 to 13.5, if we subtract, we can see that we're adding 1. And then again, we're going to add 1. So far so good. If we just look at the first 3 rows, it's like, okay, if we every 2 months, this tree is growing 1 foot. That's a constant rate of change. So like if this had been 13.5 and this guy had been something like, I don't know, 16, I'll make it easier, 16.5, so that it grew. In the first 2 months, the tree grew 1 foot, and in the second 2 months, it grew, what would that be, 3 feet. Is that right? Yeah. That's not linear, right? It doesn't have a constant rate of change, constant growth rate. So that's not what we have, though. Let's go back to what we actually have and just see if we can kind of tease out then what happens if we switch to just looking at every 4 months. So I don't know if they just got lazy measuring the tree or forgot, but anyway, so from 14.5 to 16.5, this tree is growing 2 feet, and then again, it's going to grow 2 feet. So if we look at double the months, we're also doubling our height. So I'm a math teacher, so I can kind of look at this and go, yeah, that's right, that's linear. But if you're not a math teacher, if you don't do this all the time, then it may not be immediately clear. And so if you kind of just work out then the slope, the rate of change, kind of looking, I mean, if you want to be super careful, you would look at like each ordered pair, find the slope here, and it would be 1/2, 1/2, right? Difference in the y values over difference in the x values. And then same thing going from the x equals 2 column to the x equals 4 column, it would be 1/2. And if so this is maybe we'll make a new column here, m. And so these should all be the same, right? And so then if I look at when we jumped to 4 months, well, 2/4 is indeed 1/2. That simplifies down to 1/2. And then it's still 2/4 here. All of these simplify to 1/2. So we've maintained the same slope. No matter which pair of data points we look at, we still end up with a slope of 1/2. This tree is growing 1/2 foot per month. So this is linear. Okay, so let's look at second objective. Determine whether a linear function is increasing, decreasing, or constant. So a linear function is going to be always one or the other. It's always increasing, always decreasing, or always constant because it's a straight line, right? It's not something curvy that can change. That's kind of why it's called linear. And so an increasing function tends up as you go from left to right and has a positive slope. Of course, decreasing, and we've seen this before, would have a negative slope. It's tending down. And then if you have a constant function, that's a horizontal line, and that's when your slope is 0. So remember, if you have a constant function, that just means it's just equal to a number. Okay, so let's look at example 3. And look at this kind of in words, I guess. So example 3, studies from the early 2010s indicated that teens sent about 60 texts a day, while more recent data indicates much higher messaging rates among all users, particularly considering the various apps with which people can communicate. For each of the following scenarios, find the linear function that describes the relationship between the input value and the output value. Then determine whether the graph of the function is increasing, decreasing, or constant. So for all of these, we're just going to assume 60 texts a day. So keep that in mind. Part A, the total number of texts a teen sends is considered a function of time and days. The input is the number of days, so that's like our x. The output is the total number of texts sent. So I don't know, I guess I'll use T. You could just use f of x though. So the output is total number of texts sent. So I'm going to use T of x. So assuming this teen has never sent a text prior to x equals 0, right, the beginning of the first day, then I believe our function would just be 60x, right? So we're saying they've never sent a text before. We're starting at 0. So then we don't even need to write that. And so after day 1, it's 60 times 1, 60. After day 2, it'd be 120, so on and so forth. And so, of course, this would be an increasing function, increasing linear function. So it'd be pretty steep. It's not quite steep enough, but something kind of like that. Okay. Part B, a person has a limit of 500 texts per month in their data plan. The input is the number of days, so we still got x for the number of days. And the output is the total number of texts remaining for the month. So this is just 1 month that we're looking at. So I'll stick with T of x, I guess, total number of texts, but it's remaining from the 500. So we're still assuming that our teen is sending 60 texts a day. So we're still working with 60 texts a day. So something to do with 60x somehow. But we've got to somehow work in this 500. We have a limit of 500 texts a month. I don't know what happens. Your phone just like shuts down if you hit 500. So you could think of it a couple of different ways to build your function. You could think, well, okay, if you start with 500, each day you're taking away 60, right? So you're decreasing by 60 each day. So this would be a perfectly reasonable way to write our T of x. I don't know why I wrote it all the way over here, but if we wanted to like kind of keep it in the consistent order, I guess, mx plus b, then it would be T of x equals negative 60x plus 500. And so our slope is negative 60, which means this is a decreasing function. And that makes sense, right? The number of texts that you would have remaining, you're starting at 500 and then you're going to go down. Okay, so then part C, a person has an unlimited number of texts in their data plan for a cost of $50 per month. The input is the number of days and the output is the total cost of texting each month. So this one's a little weird. You might want to pause and read that one more slowly. So input, again, number of days. That's the same x that we've been having. But now the output is the total cost of texting each month. And just to be weird, I'm going to use C for cost. Normally with cost functions, we see C of x. So, and it's just for, again, we're just looking at 1 month, just a random month. So unlimited number of texts. Doesn't matter how many text messages this person sends. It's going to cost $50 for 1 month. So it's just C of x equals 50. We don't have anything to do with the 60. In fact, it doesn't even matter how many days it is. You know, if it's day 10, October 10th, then we know it's going to cost us $50, no matter how many texts we've sent. If it's October 31st, we know it's going to cost $50 when we get our bill for October. And that's that. So this is then, of course, constant. All right. So we've got, I think, 2 more problems for this one. Yeah. So we have a couple more word problems. Interpret slope as a rate of change. So this objective. So just being able to read through kind of a bunch of verbiage and understand the slope in the context of the problem. And this is another thing we've basically done before. So example 4, the population of a small town increased from 1,442 to 1,868 between 2009 and 2012. Find the change of population per year. Change of population per year if we assume that change was constant from 2009 to 2012. We could also just say average change and not worry about whether it was constant or not, but we're assuming we have a nice linear function. This population is a linear function of the year. And so notice it says population per year. Population per year. So that's telling us that we want the population to be like the y value and the year to be the x value. So when we write down maybe our points, we would do 2009 goes with or is associated with the population 1,442 rather than the reverse order, so that when we do our slope, we'll have the correct we won't get the reciprocal of the slope, basically. If you mix them up, you'll get the reciprocal of the correct answer. Okay, anyway, 2012 then has population 1,868. So our change of population per year is our slope, and we're just going to do difference in the populations. 1868 minus 1442 over difference in the years, 2012 minus 2009. And I'm going to just put this into my real life calculator. 1868 minus 1442. Okay, I got 426. And then 12 minus 9 is 3. So 426 over 3. Let's see. And that is 142. So, I don't know, people per year, I guess. So we could say this town population increased by 142 people each year. All right, so let's look at this last one. Write and interpret an equation for a linear function. Working as an insurance salesperson, Masa earns a base salary plus a commission on each new policy. Therefore, Masa's weekly income, I, depends on the number of new policies, N, she sells during the week. Last week, she sold 3 new policies and earned $760 for the week. Let's go ahead and write that as a point. 3, N is 3, and then her income was $760. The week before, she sold 5 new policies and earned $920. So 5, 920. Find an equation for I of n and interpret the meaning of the components of the equation. So I of n, we're assuming, is a linear function. Otherwise, we wouldn't really have enough information to figure it out. But anyway, so m times n plus b. So we need, and this is a little weird using n's instead of x's, but we need to figure out the slope and then the initial value, the b value. So that's going to be kind of, well, we'll get to that. I'm giving stuff away, I guess. Okay, so slope is going to be the difference in her incomes, 920 minus 760, over the difference in the n values, number of new policies. So that's going to be what? 160 over 2. So that's 80. Okay, so then to figure out our b value, you just use one of these points. I'm going to use the first one because the numbers are smaller. And so far we know that I of n is 80 n plus b. So we can put in that if n is 3, right, this is our n, I of n is 760. So 760 is equal to 80 times 3 plus B. So now we can find our B. There's other ways to do this, but this is what I'm doing. Okay, 760 is equal to 240 plus B. So subtract 240 from both sides. We get 520. Yeah, for our B. So our final answer for this formula, I of n is 80n plus 520. Okay, so then the whole interpret the meaning thing. So basically the 80 and the 520, like explain those numbers in kind of the context of the problem. So I'll start with the 520. So I would say something like $520 is like her base pay per week. So maybe I'll say is how much she earns per week if she sells 0 policies. So you could say it multiple ways. And then 80 is basically like how much she gets on top of that base pay per policy. So she earns like an additional, I don't know, additional $80 for each new policy she sells, something like that. Okay, so that's it.